Algebra 2 honor students, this is the last day of Unit 6 here, and today we're going to be talking about absolute value inequalities and how we should be solving them. So in order to get the conversation started, we already know something about absolute value functions, and we solved in the very, very beginning of the year in Unit 1 absolute value equations. We should be able to do it graphically, which is actually how I'm going to approach this one today, and then we should also be able to do it algebraically, where once the absolute value is alone, you get to split and solve and get your two solutions that way. But to get us to get an understanding of what's going to happen with some of our inequalities today, we're going to look at this, like I was just saying, from a graphical perspective. So I'm going to type absolute value of x plus 4 into y1, and then I'm going to type 6 into y2, and I'm going to compare these two graphs. And to solve graphically, we're looking at some points of intersection. So if you go to y equals on your calculator, there's a couple ways that'll remind you of how you get to absolute value. If you hit, I believe it's alpha window actually. Yeah, alpha window is the quickest way. So your green alpha key, then window. The first choice is absolute value. There are other ways to get there, but why not do it the fastest, right? So alpha window, we're going to type in x plus 4 into our absolute value function. And then for y2, I'm going to type in y equals 6. Now, I have no idea what the last window is that I used on this particular calculator. So I'm going to zoom 6 to graph over that standard viewing window there. And I get that V-shaped absolute value that we know what that looks like. And then I see the line y equals 6 come across the way. Now, I'm pretty sure I can see that point of intersection over here for my first solution on the left. But to make this a little bit easier to see, if you hit the window button, maybe it would benefit us to go further to the left on the x-axis, which would be requiring us to change the x-min. So for example, if I maybe move out to negative 15 for your x-min, that should give you just a little bit of a better view. And now you can really clearly see those 2 points of intersection nicely there. So I'm going to go ahead and maybe make a quick sketch of what this looks like. And by the way, no surprises here, right? I mean, this is an absolute value that gets shifted to the left 4 units. So here's my vertex. Okay. And if I want to know when we're hitting the line y equals 6, sorry, my V got a little off there, guys, but you get the idea. Here's the line y equals 6. We have that happens in 2 different locations. So my solutions are, where are these 2 values on the x-axis? So to calculate those intersection points, you're going to hit second trace, and we're going to choose option 5 for intersect. Doesn't matter which order you do them in. I'll do the one on the left first. So let's see, we get 1, 2, 3. You got to hit enter 3 times when you get near the intersection. This one occurs when x equals negative 10. And then if I repeat that process, second trace, we're going to calculate the intersection on the other side. Let's see. So if I come near this point of intersection, hit enter once, twice, 3 times, that occurs at x equals 2. So the solutions, or if you want to write it as a solution set, would be negative 10. Oops, I need another curly bracket there. So negative 10 and 2 are the solutions where the absolute value of x plus 4 is equal to 6. All right, so then if I have this graph in front of me like we currently do, what if I said, well, where is the absolute value of x plus 4 greater than 6? Well, it's greater than 6 where the absolute value function is above the line y equals 6. So notice that happens when I'm to the left of negative 10 or when I'm to the right of x equals 2. The absolute value function goes above the line y equals 6. So this would be from an interval notation, negative infinity to negative 10, union 2 to infinity. And on the other hand, if I wanted to solve when is this less than 6, maybe I'll even throw in a little less than or equal to there. We can include these endpoints then, right? So for less than or equal to, we can say that, oh, the absolute value is below the line y equals 6 in between negative 10 and 2, like that. So the whole point of today is, of course, we can do this pretty easily graphically, but what is the algebraic way of going through this process? And it happens to involve some partitioning. So partitioning we saw in the day 4 video for the first time, but today our main focus is, how do we do this algebraically? So we're going to write down some steps that we can use. And I'll tell you, for the partitioning, to figure out what we're partitioning around, you're going to set whatever the inside of the absolute value is equal to 0 to find the critical values. Critical values are the ones that we put on our number line in order to partition. And what happens is, once I put them on the number line for partition purposes, we're going to set up inequalities in each region by determining positives and negatives. So we did a little bit of positives and negatives yesterday, and I'll tell you, positives and negatives today will look a little bit different in terms of the way we use that information to solve the inequality. All right, but once I've set up in each region what's going on there, we're going to solve the inequalities and write answers in interval notation. So I want to solve one that we've already know the solution to, so we can see what the algebraic process looks like. And what I'm going to solve is I'm going to figure out, when is the absolute value of x plus 4 greater than 6? We already know what the answer is. Let's see what the algebra looks like through this partitioning process. So here's our example. Absolute value of x plus 4 is greater than 6. Well, step 1 says set the inside of the absolute value equal to 0 to find the critical values. I mean, that you can probably do in your head in a lot of examples, but that would give me that x equals -4. So I'm going to come down here, and I actually want you to give yourself a little bit of space when you draw your number line to partition here. Okay. We're going to split this up into 2 regions. Okay. One thing's happening to the left of -4, something's happening to the right of -4. Here's what we have to do next. It says set up inequalities in each region based on where you have positives and where you have negatives. So to the left of -4, if I pick -5, plug it into the absolute value expression, -5 plus 4 is a negative number. And then what will happen on the other side is we'll most likely get positive, right? If I test something like 0 out here, 0 plus 4 is a positive number. So how does that help me to figure out what's happening in these sections? When you get something that's negative, the inequality that you're going to solve on this side is the negated form of this expression. So when you get negative, you can drop those absolute value bars and solve -x minus 4 greater than 6. Because think about it this way. If you take the absolute value of a negative, doesn't it make it into a positive? So what I'm telling you is that no matter what you pick over here, it's going to be a negative number. How do we change it to positive? By negating it. So when you get negative in your partition region, you have to negate the expression inside the absolute value to solve over here. Meanwhile, when it's positive, the absolute value of a positive number stays positive. So you can drop the absolute value bars on the right side of -4 and just solve that as is. And let's see what happens when I solve on each side. Here I'm going to get that -x is greater than, add the 4 over, so that's now 10. Just be really, really careful here. When you divide by -1, you now get x is less than -10. Make sure you got less than, because we flip the inequality when you divide by -1. So you can go ahead and put -10 on a number line. Values of x that are less than -10 are everything to the left of -10. Really quickly over here, if I subtract 4 from both sides, you wind up getting that x is greater than 2. So you can put 2 on the number line, and x values greater than 2 are everything to the right of 2. So now that we've solved each of these inequalities and we've shaded on the number line here, my answer and my solution in interval notation is -infinity to -10, union 2 to infinity. And that's exactly what we got up here a second ago when we confirmed our answers graphically. So this algebraic technique will always work for us. That if you find the partition points, determine where we're positive, where we're negative. If it's negative, drop absolute value and negate it. If it's positive, drop absolute value, leave it exactly the same. All right, let's get into some more practice here. So for number 2, let's determine when is the absolute value of x plus 3 less than or equal to 16. Okay, well, first thing I have to do is figure out what am I even partitioning around. Set that inside of the absolute value equal to 0, and you get x equals -3. Okay, so -3, that's what's going to go on my number line is my partition value. Okay, so put that kind of right in the middle there. And I have to test now a number on either side of -3 and see what's happening here. If I test -4, -4 plus 3 is a negative number. If I test, let's say 0 again, 0 plus 3 is a positive number. So what I get to do on the left side here is when I see negative from the partitioning, that means drop the absolute value and negate the whole expression. -x minus 3 is less than or equal to 16. We're going to solve that in a second. Over here, since we get positive, you can drop absolute value and leave it exactly the same. Okay, so now when I go to solve, I'm going to add the 3 to this side. So -x is less than or equal to 19. Really carefully, divide by -1 to get x is now greater than or equal to. Flip that inequality. Don't forget to divide this by -1. Sometimes you can just write 19 there, but it's really now -19. Okay. I can really quickly subtract the 3 over in this one and get x is less than or equal to 13. So I want you to think about what this is going to look like. I need x to be bigger than -19, but less than 13. So as compared to the shading and in the last one, remember in the last one it went on the outside here, according to those inequality signs. What's going to happen in this case? Well, to be bigger than -19 means shade to the right. To be less than or equal to 13, we're going to shade to the left. So it turns out to make this true, you're going to shade everything in between those two solutions, -19 and 13. So your solution to this overall inequality is with brackets, -19 to 13. Any numbers in between those, including those endpoints, would satisfy that inequality. Now, here's one of the big differences that maybe you've noticed already. As compared to yesterday's partitioning, the partition points were always a part of the end solution yesterday. Right? Wasn't I finding the values yesterday that whatever they were on the number line, they always kind of fit with the solution in the end? Notice how this is just helping me set the stage to solve these inequalities, but I just shaded right on through -3, guys. And you don't put an open circle there, don't put a closed circle there. It's just the point that helps me to split this up. The actual solutions come from whatever you get in each of these regions, which feels different than yesterday and does take some time to get used to. All right, we're going to try and squeeze 2 more examples in here. So for number 3, we get absolute value of x plus 2 is less than the absolute value of x minus 4. We want to solve this one. So this is a double absolute value. This is going to be a little bit more intensive for us in terms of the partitioning. Because instead of having one critical point to partition around, we now have 2 critical values. You're going to set each of these equal to 0 to figure out what are the 2 points that we're going to wind up partitioning around. Okay, so draw a big number line down below. I mean, you could do this real quickly in your head, can't you? X equals -2 and x equals 4 would be the critical values. So -2 goes here, 4 goes there. Okay. So draw those partitions in and then say, all right, let's pick something to the left of -2. You have to plug it into both of these to see, are we going to keep the absolute value quantities the same, or are we going to negate them? Okay, but test -3. -3 plus 2 is negative. -3 minus 4 is negative. So the inequality that we solve out here is dropping those absolute values, but negating both of these. So it's going to be -x minus 2 is less than -x plus 4. Drop the absolute value, negate both. Before I solve that, let's just come over to the middle, see what the rest is going to look like. If I pick 0, 0 plus 2 is positive. 0 minus 4 is negative. So here's kind of a split. When I drop absolute value for the first one, since it's positive, you can leave it as x plus 2. When I drop the absolute value on the other side, since that would return a negative number, you need to negate the expression -x plus 4. Finally, to the right of 4, if I pick x equals 5, 5 plus 2 is positive, 5 minus 4 is positive. So in the last region, you can actually just drop those absolute value bars and solve the inequality as is. Okay. Now that we've set up the inequalities we're solving in each of these sections, let's see what winds up happening. Over here, if you add x to the other side, something really weird happens. These x's cancel, but so do those. And you get -2 is less than 4. Is this true or is this false? Take 5 seconds and really think about it. I mean, -2, yeah, it's definitely less than 4. This is always true. What does that mean for us in the end? I'm going to hold off on it, but what it actually is going to mean is that every number in this section would satisfy this inequality. You'll see why that's the case in just a second. Let's come over to the middle section. If you add x to the other side, now it's a 2x on this side, right? Add this x over here. Subtract the 2 to that side, you get 2x is less than 2. Some really careful algebra there. Divide both sides by 2 to get that x is less than 1. So since 1 is in between -2 and 4, put it on the number line. It's going to have an open circle because it's only less than 1. And less than 1 is to the left. And notice how when I start shading to the left, I'm going to eventually go through that partitioned area and say, you know what? Hey, we knew that everything in this section worked. So that's what we'll see when you start getting these sections that sometimes are always true like that. And that's weird, guys. I know that feels a little bit weird. Okay, since this is always true, you can shade everything out there. You don't have to stop at -2. -2 is just helping me set this up, but it's not an actual part of the end solution, okay? What's happening out here to the right? Well, if I subtract x from both sides, oh wait, this weird thing happens again where the x's go away. And over here, I get 2 is less than -4. Well, we get a really similar case over here, right? This was always true. What about 2 less than -4? That's never true. So how do I take that result and interpret the context of this problem? It means that nothing out here will be a solution to this inequality. No matter what happens in this region, nothing will satisfy this inequality over here. So the only solution that I get in the end is that any x value from -infinity to 1 will satisfy this inequality. Okay. And that's pretty much it. And if you think about what the graph looks like, by the way, if you were to graph it on the calculator, absolute value of x plus 2 gets shifted 2 to the left. Absolute value of x minus 4 gets shifted 4 to the right. Okay, and they intersect at x equals 1. So where is this absolute value of x plus 2 less than x minus 4? Anything to the left of 1 makes this true. But as soon as I go to the right of 1, notice how the purple graph is now going to always be above the pink graph. Okay. So because that happens graphically, this solution algebraically does match up with what the graph would suggest about that. And we know exactly what those look like without doing really much on the calculator at all. Let's do one more just for good measure. This is a tough process in general, guys. So if you have questions next time I see you, I encourage you to ask those. Of course, when we do our recap, we'll do some more practice with this, but absolute value of 5x minus 2 is less than or equal to the absolute value of 3x plus 4. It's the last one we'll work on now. Okay, we need to decide what are our critical values. Maybe a little bit more algebra involved to set each of those inside parts equal to 0, but hopefully you would get that this is x equals 2/5 and this is x equals -4/3. If you have to off to the side do this to solve, there is no shame in that. Please make sure you have the correct partition points. All right, so I'm going to put my number line down here to give myself some space. And I said -4/3 was one of the partition points. The other one is +2/5. Okay. So if I pick values in each of these regions, I'm going to start deciding, do I drop the absolute value and negate it, or does it stay the same? All right, let's talk about to the left of -4/3. Just be careful there. -2 will work just sufficiently, right? 5 times negative 2 minus 2 is a negative number. 3 times negative 2 is negative 6, plus 4 is a negative number. So then what's going to happen is I'm going to drop those absolute values, but negate this and negate that. Negative 5x plus 2 is less than or equal to negative 3x minus 4. Okay. Come over to the middle. 0 is a great option. If I plug in 0 to this function, we're going to get a negative result. 3 times 0 plus 4 is a positive. So when I see negative, drop the absolute value and negate negative 5x plus 2. But where it's positive, you can drop the absolute value and leave it exactly the same. And then to the right of 2/5, if you pick 1, you'll get positive and positive. Hopefully you'll just trust me on that. If you check it, you can check it pretty quick. So then in the last section, you can drop those absolute values and leave it exactly as it currently looks. And now we're at the stage where we're going to solve each of these and see how that works out on the number line down here. Okay, so in this one, I always like putting x on this side no matter what. Because in the end, if I have x is greater than something or x is less than something, that tells me which way to shade on the number line, okay? That could be personal preference, but I think it will help you as well to do that strategy. So the reason I say that is maybe you would add a 5x to the side to make it a positive. I like adding the 3x over here just to keep x on the left. So that means I have to subtract 2 over here to make that a negative 6. And when you divide by negative 2, the sign does flip to greater than or equal to. Negative 6 over negative 2 is 3. Well, here's the thing. 3 is not in this section to the left of negative 4/3, is it? I can't just plop 3 on the number line right now because it's not to the left of negative 4/3. So I have to decide, are the x values in this region always bigger than 3? Or equal to 3, which we know it's not equal to 3. But are the x values in the section always bigger than 3? The answer is no. Nothing that I pick in this region would make that true, that the numbers are bigger than 3. So therefore, we're not going to shade anything out here. There's no solution to this overall inequality to the left of negative 4/3. Let's go over to the middle and see what happens here. I'm going to, again, subtract the 3x over here to make it a negative 8x. Subtract the 2 over here to make that a positive 2. When you divide by a negative, flip that inequality around to get x's greater than or equal to. 2 over negative 8 can reduce to negative 1/4. Does negative 1/4 fall between these values? Absolutely. So put negative 1/4 on the number line. We can include it with a closed circle because of the equal to part here. Where are the values greater than negative 1/4? To the right. So you can start shading to the right. Most likely, you're going to get a point that it connects to out here. A stopping point. We'll confirm that in a second here, but I wouldn't shade to the right forever quite yet. We still want to see what's happening in this section over here. So in the last section, subtract 3x to this side to make it a 2x. Add the 2 over to this side to make it a 6. And now I get x is less than or equal to 3. We kind of got something similar looking over here. But this makes a lot more sense. First of all, 3 is a number that is to the right of 2/5. So I can put that on the number line. Where are the values less than 3 in this section? It's shading backwards to the left. So then notice how it connects to the solution of to the right of negative 1/4. And my final answer for number 4 is bracket negative 1/4 to 3. And it's a pretty methodical process, but I understand conceptually this is tough. So next time I see you, I promise we'll do more practice. You'll let me know what questions you have, and we'll go from there. Have a great day.